Hello and welcome back to Homework Help for Math 2. This time we're going to be looking at Unit 8, Circles, Angles, and Shapes, Lesson 9, Summing Up Sandcastles. Starting with the Ready section. The directions here say the height of an arrow shot upward from the Earth's surface at an initial velocity of 40 meters per second can be modeled by the function f of t equals negative 5t squared plus 40t. Notice that our velocity appears here. And in case you're wondering, the first term, the negative 5t squared, that is the effect due to gravity. So the two things that are sort of factoring into the path of this arrow here is that you have your initial velocity, so that's plus 40t, it's going up. And then the force due to gravity is negative because the gravity is pulling it down, so it's negative 5t squared. That's where that equation comes from. Question 1 says, calculate the number of seconds the arrow will be in the air. So there are multiple ways of doing this problem. The important thing to recognize is that our function here, specifically f of t equals negative 5t squared plus 40t, that tells us the height of the arrow. And so if we want to know how long it's in the air, basically we want to know, well, what is the difference in time between when the arrow is on the ground? Excuse me. So the arrow is going to be on the ground when we start, and the arrow is going to be on the ground when it hits the ground, obviously. And we want to know, well, how much time elapsed between those two time periods. So because this function gives us our height off of the ground, if we decide that, if we say f of t, which we are told equals negative 5t squared plus 40t, all I've done is I've just rewritten our function. If we say, well, what happens when we set this equal to 0, right? This is saying our height of the arrow is 0. It's the result of the function. And now I want to know, all right, well, what's the value or values of t that result in 0? Now, there are multiple ways of solving this equation. If you take a sneak peek at number 2, you can see one possible solution for number 2. And if you jump all the way to the end, it actually turns out that t is 0 and t is 8. So we kind of sort of already know our answer to number 1, but let's make sure that we understand how to do this without relying on, work that's just provided for us in a subsequent question. The method that is shown in question number 2 is totally valid and totally works. It's completing the square. So you can see here that they identify this as completing the square. For number 1, there is an easier way to solve number 1 that still gets us our correct answer that does not involve completing the square. And so that's actually the method that I'm going to use for number 1, because it doesn't say how to solve it. It just says solve it or calculate. So what I'm going to do for number 1 is I'm going to take a look, and what I notice is that I have a GCF here. So we have negative 5t squared, and then we have 40t. Now, one of our terms is negative and one of them is positive. For reasons that we could get into, I'm going to factor out the negative. So if you don't factor out the negative, it's actually not a problem, but I'm going to factor it out because I think it's going to make our job just a little bit easier. So I'm going to factor out the negative. Then we have 5 and 40. Well, the GCF of 5 and 40 is 5, because 5 goes into 5 once and 5 goes into 40 8 times. Then we have t squared and we have t. Well, the GCF of t squared and t is t. So my GCF here is negative 5t. When I factor that out from both terms, my first term was negative, so it stays the same. It stays positive, essentially, because I've already dealt with the negative. I've already dealt with the 5. The only thing that's remaining is we have this t squared, and I factored out a t. Well, that means that there's a single t left over. And if you go backwards, t times t is t squared. All right. Now my second term is positive, but I factored out a negative, which means I need a negative so that when I distribute, I get a positive. I factored out a 5 from 40. That leaves me with 8. And then I factored out a t, and I started with t, so there's nothing left to include, and this still equals 0. Now, what we have is we have something times something equals 0. So we have a product that equals 0. The zero product property tells us that if you have two things and you multiply them and you get 0, the only way that that can happen is if one of the things that you multiplied itself equals 0. To put that another way, it is impossible for you to take two non-zero quantities and get 0. So what this equation tells us is that either negative 5t has to equal 0, or t minus 8 equals 0. Right? This will always be true when you have a product, when you have a multiplication of two things and your result is 0. You can set each factor equal to 0 and then solve. So for the first one, if we divide everything by negative 5, we get t equals 0 divided by negative 5, which is still 0. Now, hopefully this result sort of makes sense, because this is just another way of saying that at the very beginning, instantaneously at the very beginning, before we shoot the arrow, sort of the assumption in this problem is that the arrow is on the ground, right? Now, presumably, if someone's holding the arrow above the ground, it's like a couple feet off. But for the purposes of this question, we're just going to make the assumption that the arrow is literally on the ground. Our other equation, if we get t by itself, we'll add 8, and we get t equals 8. What this tells us is that, all right, well, the arrow started at time 0 was on the ground, and then also after 8 seconds have elapsed, the arrow is back on the ground because of gravity. So therefore, our final answer here is 8 seconds. So our arrow spent 8 seconds in the air. It had a velocity of 40, but eventually gravity sort of overpowered the velocity, and because of gravity, this arrow did not escape Earth's orbit. It did come back to the ground, and it took 8 seconds to come back to the ground. All right. Question 2. Question 2 says, if you used completing the square on f of t to find the elapsed time in problem 1, your work would have looked something like this. Now, if you want to, you are welcome to sort of skip what I'm about to say. I'm going to try to do this quickly. I'm going to try to run through the process of completing the square and sort of like why this works the way that it does. If you're not interested in this, but you still want to know how to do this question, you're welcome to kind of skip ahead a little bit. But I'm just going to try to walk through how we complete the square, because it looks like this. And you'll have to decide for yourself and maybe talk to your teacher about how important it is for you to understand how to complete the square. So we start with our the same initial equation that we had with number 1. So 0 equals negative 5t squared plus 40t. Now, the first thing we have to deal with is we have to deal with this negative 5. Because when you complete the square, you need your immediate coefficient on the squared term, you need it to be 1, right? You need it to be an invisible 1. So notice that our first real step here is we factored out the negative 5. So our second equation becomes 0 equals negative 5. We're locked into that. You have to get rid of that negative 5. When you factor out the negative 5, notice that now our coefficient that's directly on t squared is 1. It's an invisible 1. That's what we want, and that's great. Now we have to factor out that negative 5 from 40 as well. So when you factor out a negative 5 from positive 40, you're left with negative 8. And then we know that when we're completing the square, we have to add something. So we've sort of left open this spot for whatever the something is. Now, the something that we want is going to be our coefficient on t, which is negative 8. We want half of that, and then what we're going to do is we're going to square the result. So negative 8 divided by 2 is negative 4, and negative 4 times negative 4 is positive 16, and that's where this positive 16 comes from. It is half of the middle term, and then you square the result, and that gives you 16. Now, you are not allowed to just randomly add or subtract things to one side of the equation. So because of that, notice that when you add the 16 here, notice that it's still getting multiplied to the negative 5. So what you're really doing is you're subtracting 5 times 16. You're not allowed to just do that randomly without doing it on the left, and you don't want to do it on the left, which means to balance it, you need to sort of add it back in. So what's happened in our third step here is we have subtracted 5 times 16, and so now we have to also add 5 times 16 in order to maintain the balance in this equation. All right. Going to the fourth step, notice that we've been able to take our trinomial, the t squared. So we've been able to take this guy right here, the t squared minus 8t plus 16, and we've actually been able to rewrite that as a binomial squared. And this is how completing the square works. If you do this correctly, you can rewrite your quadratic trinomial as a binomial squared. And specifically, it's going to, the t squared is going to become t, and then this term, the negative 4, is this term right here, which is the negative 4. And you can prove all of this by using FOIL, but we're not going to do that right now. So we can rewrite our quadratic as a binomial squared, and then 5 times 16 is simply 80, which is just sort of hanging out at the moment. If we bring that 80 over to the left, so we subtract 80, so that's where that negative 80 comes from, and then the right-hand side doesn't change. Now, we want to get t by itself, so we want to deal with this negative 5. We could have dealt with the negative 5 before now, but we're dealing with it now. So you divide both sides by negative 5. Negative 80 divided by negative 5 is positive 16, and the negative 5 on the right goes away. So now, in order to get t by itself, we need to take the square root of both sides. So the square root of 16 gives us 4, and the square root of t minus 4 squared is t minus 4. We need a plus minus here because we are unsure as to whether the original t minus 4, whether that was positive or negative. It could have been positive, it could have been negative, but when you square it, you get a positive no matter what. So when you take a square root like this, you need to introduce the plus minus because we're not sure whether the thing that we squared was positive or negative in this case. So we have our plus minus, so plus or minus 4 equals t minus 4. If you add 4 to both sides, you get t equals 4 plus 4, which is 8, and t also equals 4 minus 4, which is 0, giving us our final answer of 0 and 8. So, like I said, that was a very, very quick, sort of superficial rundown of how we complete the square. If you are not comfortable with completing the square and you are concerned that is something that you sort of need to know moving forward, I would encourage you to check in with your teacher and sort of figure out the best way to get some additional practice with completing the square. So, the remaining directions say use f of t equals negative 5 t minus 4 squared plus 80. So I'm actually going to erase all of these notes and all this other stuff. And notice that they're talking about this piece right here. Okay? So we're talking about once you got to that step, and we sort of let that equal f of t. So use that to explain why the maximum height of the arrow is 80 meters and the height was attained at 4 seconds. So just sort of explain why this works, is what this question is ultimately asking us. So we can go ahead and, I think, type this. So as I'm setting up the box here, what we're looking for is sort of an explanation as to why this all makes sense. So in f of t, in f of t, the maximum value of the first piece, so -5 parentheses t minus 4 squared, is 0. The reason is because what we have is we have something squared, which is guaranteed to be non-negative. It's either 0 or positive. But then we multiply that by -5, which means it's guaranteed to be non-positive. It's either going to be 0 or it's going to be negative. So the maximum possible value for that thing is 0. If you don't believe me, go ahead and try it out. Try plugging in different values for t, and every single value you get for t is either going to be a negative number or it's going to be 0. You cannot get a positive value if you plug in a real number for t. So the maximum value for that is 0. Therefore, the maximum value for the whole thing, which is -5 t minus 4 squared plus 80, is 80. So if the maximum value for the first part is 0, then when you tack 80 onto it, then the maximum value for that's going to be 80. So that tells us that the maximum height is 80, no matter what the time is. When the height is 80, -5 parentheses t minus 4 squared must equal 0, because that's the top. That's the top of the height function here, which it does when t equals 4. So I think that's sufficient for our purposes here. And again, notice that if you were to try plugging in other values for t, right, if you say like t equals 3, well, that's going to cause f of t to be less than 80. If you say t equals 5, if you say t equals 5, that's also going to result in an f of t value that's less than 80. So any value other than 4 is going to give you a result that's less than 80. So the height occurs, first of all, the height is 80, and that occurs when 4 seconds have elapsed, because that's just the way that this function works. Okay. Next set of directions say, use the following information for problems 3 through 5. The height of an arrow shot upward from the Earth's surface at an initial velocity of v meters per second can be modeled by the function f of t equals -5t squared plus vt. So this is very similar to 1 and 2, except now it's just saying, well, whatever your initial velocity is, which in this case is v, just make it your coefficient on your t term, and then that gives you this function that tells you the height of the arrow. For each problem, calculate the number of seconds the arrow will be in the air for the given velocity, and then use completing the square, so it's telling us to complete the square here, to find the maximum height of the arrow and the time it takes to reach its maximum. So we'll start with question 4. Question 4 gives us an initial velocity of 100 meters per second. So we have 100 meters per second. And our first set of directions here say, calculate the number of seconds that the arrow will be in the air. So the directions here did not give us any specific criteria for how we solve this equation. So we may as well solve this in a slightly easier way than completing the square. So I want to know how long it's going to be in the air, and we're assuming it starts on the ground. So we can take our function, which is negative 5 t squared plus, now it says v times t, but for question 4, our v is 100, so we're going to plug in the 100. We're not going to plug in v, we're going to plug in 100 t, and I want to know, when does this equal 0? When is the arrow going to be back on the ground? All right, well, there's not a lot of space here in this problem. I'm going to factor out a negative 5t. I'm going to try to squeeze it in below here. So I'm going to factor out a negative 5t, just like we did in question number 1. When I factor out the negative 5t, so the negative 5 is just negative 5, t squared, I factor out a t, I'm left with a single t. Here I have plus 100, but I factor out a negative, so I need minus. 5 goes into 120 times, and then I factor out a t from t, so I'm left with just 1, and this whole thing still equals 0. Zero product property tells us that either negative 5t equals 0 or t minus 20 equals 0. If I divide by negative 5, I get t equals 0. That just sort of confirms our assumption that the arrow starts on the ground. And over here, I get t equals 20. And so that tells us that the arrow will be back on the ground after 20 seconds. It's in the air for 20 seconds. At that point, the arrow is back on the ground. So that's our answer for 4A. For 4B, the directions explicitly say, use completing the square to find the maximum height of the arrow and the time it takes to reach its maximum. So we are going to start with the same initial equation. So we're going to start with negative 5t squared plus 100t equals 0. Now, to complete the square, your coefficient on t squared must be 1, which means we have to factor out the negative 5. Only the negative 5, not a t, but we have to clear out the negative 5 to get sort of a nice clean t squared, which is now what we have. We have to also factor it out from the 100t. When you factor out a negative from a positive, you're left with a negative. And 100 divided by 5 is 20. And because I did not factor out a t, I still have a t here. Now, I know with completing the square, I have to add something. I don't know what that is yet. And this still equals 0. So when I'm completing the square, I essentially just rewrite everything that I have. And what I want, I'll do this over here on the left, is I want to take my middle term, which is negative 20. I want half of that, and I want to square it. So half of negative 20 is negative 10, and negative 10 times negative 10 is 100. And so what I'm going to do here is I'm going to add 100, close parentheses. Now, notice that because it's inside the parentheses, I'm going to end up multiplying that by negative 5. So what I'm really doing here is I'm subtracting 5 times 100. But if I subtract 5 times 100, in order to maintain balance, I have to simultaneously add 5 times 100. Because you can't just randomly add or subtract on one side without doing anything on the other side. So this still equals 0. When you complete the square, this simplifies to just t, and then the number that's going to go inside the binomial is this number right here. It's half of the middle term. So this becomes t minus 10, close parentheses, and now my squared is on the outside of the parentheses. Again, this is the process for completing the square. 5 times 100 is 500. and that equals 0. And at this point, we can stop. We can stop here because it says use complete the square to find the maximum height. Well, the maximum height, this piece of my equation, the largest that value can be is 0, because no matter what I plug in for t, I'm going to get either 0 or a negative number. So that's kind of capped at 0, which means my maximum height is this guy. So my maximum height is 500 meters. And then the time that it takes is when this equals 0. Well, this equals 0 when t equals 10, because 10 minus 10 is 0 and everything cancels out. So that means that the maximum height, so the max is 500 meters at t equals 10 seconds, which in this case also happens to be half of our answer for A, which was 20 seconds. As long as you start and stop on the ground, that will work. However, if you start from, like, let's say, like the top of a building and the arrow ends up on the ground, it will not be half. But in this case, because you're starting on the ground and you're ending on the ground, it turns out that it is in fact half of your answer for A. So the maximum height occurs 500 meters after 10 seconds have elapsed. Moving on to the set section. Directions here say, for each of the following, write out the sum of terms represented by the notation, then use the formula you derived in class today for the sum of a geometric series to find the total of the sum of the terms without adding each term individually. So the point of this exercise is to, first of all, identify, if we didn't have the formula, what would we need to add? What are all the different things that we need to add together? And then B is saying, all right, don't do that. Don't actually do the addition. Use the sort of handy-dandy formula that we developed to actually save some time instead of having to, add every single little thing that ends up getting listed. We will start with question 6. So question 6 is given to us in sigma notation. And question 6 is saying, take the sum from k equals 1 to n of 1/3 times 2 to the k minus 1. And part A says, write out the sum of terms represented by the notation. So our sum is, if you want to, I guess you could rewrite the summation. So we're talking about, again, this, I don't want red. So our sum, I'm going to write it the way that it sometimes appears. K is 1 of n of 1/3 times 2 to the k minus 1. Okay. So the way that sigma notation works is you essentially start with that value right there. So in this case, it says k equals 1. That means that we're going to start with a k value of 1. So when I take my expression here, which is 1/3 times 2 to the k minus 1, what's going to happen when I plug in for k? And remember, I'm plugging in a 1. Well, our exponent is k minus 1, which means if k equals 1, we get 1/3 times 2 to the 1 minus 1, which is 0 power. So if you're not that comfortable with sigma notation, I would kind of pause here and just make sure that you understand where this first addition, this first term came from. We're starting with a 1, because that's what our sigma notation tells us. It says k equals 1. And when you plug in for a 1, your exponent becomes 1 minus 1, which is 0. Now, this is sigma notation, which means we're going to then add the next term. The next term, oh, I mistakenly put an n here. This is supposed to be a 10. So we're going up to 10. So with sigma notation, we repeat what we just did until we get to our final value of 10. And we're just going to increase by 1 every single time. So we started with 1. Well, the number after 1, spoiler alert, is 2. So what that means is I'm going to do the same thing, 1/3 times 2, but now it says, again, k minus 1, but now our k value is 2, because it's the next term after 1. Well, when I plug in a 2, I get 2 minus 1, which is 1. And again, if you're not that comfortable with sigma notation, I would pause and try to understand what is it that we're doing here, and where are these terms coming from? Let's keep going. We're going to add 1/3 times 2. Well, we started with 1, then we did 2. Our next k value is 3. I plug in a 3. I get 3 minus 1, which is 2. And I keep going. If you really wanted to, you could write out 1/3 times 2 to the 3rd, plus 1/3 times 2 to the 4th, plus 1/3 times 2 to the 5th, plus 1/3 times 2 to the 6th, plus 1/3 times 2 to the 7th, plus 1/3 times 2 to the 8th. However, I think we get the point. So I'm actually going to jump all the way to the end, and I'm going to write my last term. So we did ... plus. Now I'm going to jump right to the end. So our last term, as always, is going to be 1/3 times 2. Our last term involves this number, 10. So I'm going to take that 10, I'm going to plug it in, and I get 10 minus 1, giving us 9. So this is our sum. Personally, I think that is sufficient for this question. I don't think we need to sort of like simplify it, but I'm going to do this in, well, here's what I'll do. I'll say this is our answer, as far as I'm concerned. However, the book also cleaned it up a little bit, so I'll go one step farther. If I take a look at my first term, 1/3 times 2 to the 0, well, 2 to the 0 is 1, because any non-zero value is 1. So 2 to the 0 is 1, and 1/3 times 1 is simply 1/3. So our first term is really just 1/3. Plus, now our second term, 2 to the first is just 2, and 1/3 times 2, well, 2 kind of smushes up into the numerator, and I get 2/3. Plus, my third term, 2 squared is 4, and 1/3 times 4 is 4/3. Plus, ... plus, 2 to the 9th is 512, I want to say. And 512 times 1/3 is simply 512 divided by 3. So if you write your answer like that, I guess that's better. Maybe your teacher wants you to plug in for all of the values. Because of space, I just did the whole ... thing. But if your teacher wants you to write out every single term, it's not that difficult. You just kind of keep doing it over and over. So really just limited by the amount of space that you have. Now, part B. Again, I'll read the directions. It says, use the formula you derived in class today for the sum of a geometric series to find the total of the sum of terms without adding each term individually. So at this point, if you wanted to, you could bust out your calculator and just sort of add up all of these things. However, sometimes in math, we like to be a little lazy. We have our formula. And just as a reminder, our general formula, S sub n, is, I want to make sure I use the same notation as the book. So the book writes it as a times r to the n minus a over 1 minus r. Occasionally, you might see this written in a similar but still mathematically valid, but maybe it might look a little different method. But in this class, we're writing it like this, which is fine. So all I need to do here now is I just need to plug in these different values. So if I go back to my original sigma notation here, A is essentially it's the coefficient. It's this term right here. It's the 1/3. So A is 1/3. R is our common ratio. It's the thing that's getting raised to the exponent, which is 2. And then, what are we missing? N. Well, N is how many terms we have. It's the number of terms. If I start at 1 and I go to 10, well, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 terms. I will say as a shortcut, with sigma notation, if you start at 1, then this value will be n. But that's only if you start at 1. If you do not start at 1, your n value is not the number above the sigma. It's something else. You need to sort of calculate it. But if you start at 1, which it looks like we're always doing, which is nice, if you start at 1, then your n value is just whatever the top number is, which is 10. So now I'm just going to take this, I'm going to plug in. So, actually, I guess technically we should say this is now, so this becomes S sub 10. Notice that now I have a specific partial sum. My A value is 1/3. My R value is 2. It's probably a good idea to put that in parentheses, even though it's not strictly necessary. Just make it, abundantly clear what has the exponent on it. Raise that to the n power, which is 10, minus A, which is still 1/3, over 1 minus my R value, which is 2. All right. So this is my, wait a minute, hold on. Did I get that back? No, I'm sorry. I have to fix this. Apologies. I thought that looked wrong. It is R minus 1. Okay, that looks better. And so R is 2 minus 1. All right. So if you happened to notice that error before I saw it, kudos to you. Now, I think that the easiest way to do this, I would use the calculator here. I guess we could do this without using the calculator, but I don't feel like it. So notice that our denominator is just 2 minus 1, which is 1. So realistically, all we need to do is evaluate the numerator, and then we're done. And the way that I'm going to do that, I'm just going to jump to my calculator right here. So I have a 1/3. It's a little overkill, but whenever you have a fraction, it's not a bad idea to put it in parentheses. It turns out it's not strictly necessary for this problem, but I want to do it anyway. Also not strictly necessary is the next set of parentheses, but I'm going to do it anyway. We're going to raise that to the 10th power. I get out of my exponent. And then we are subtracting 1/3. And we end up getting 341. Now, again, I went a little heavy on the parentheses there, but I think that's just to, again, with fractions, you want to be careful, and with exponents, you want to be careful. So if you got 341, that is correct, even if you didn't format it exactly the way that I did. So our answer here, using our handy-dandy formula, is 341. If you were to go back to our sum in green and type all that in, you would get 341. It's just going to be kind of, a little monotonous and easily prone to mistakes if we don't use our summation formula. All right. Question 8. So question 8, same directions, just a different sigma notation. So this time we're being asked to find the sum as k goes from 1 to 5 of 4 times 1/2 to the k minus 1. And again, the first half of our directions say write out the sum of terms represented by the notation. So what we're talking about here is we're talking about the sum as k goes from 1 to 5 of 4 times 1/2 to the k minus 1. We're being asked to write out the terms, and it says we start with a k value of 1. So when I rewrite my algebraic expression here, I get 4 times 1/2. Now I'm starting with a k value of 1. So when I plug in a 1, I get 1 minus 1, which is 0. It's sigma notation, so I add, and I do it again. 4 times 1/2 to the, now I started with 1, so my next input for k is 2, and 2 minus 1 is 1. Plus, again, 4 times 1/2 to the, my first k value was 1, my second one was 2, so my third input is 3. When I plug in a 3, I get 3 minus 1, which is 2. And this will continue. Now, it turns out that in this one there's only 5 terms. So I guess, unlike 6, I'm not going to do the whole ... thing. I'm just going to go ahead and write all 5 terms. So let's just wrap this up. 4 times 1/2. Hopefully you're noticing a pattern here. My k value went 1, 2, 3, now it's 4. My exponents are 0, 1, 2. So when I plug in a 4, I'm going to get a 3. And then my final term, and I know it's my final term because now I hit my 5, right? Once I hit that value for k, that's my last term. So I did 1, 2, 3, 4. I'm up to 5. This is going to be my last one. So I add 4 times, parentheses, 1/2. My input is a 5, and 5 minus 1 is 4. And so that is my exponent. And really, that's my answer. So that is my sum. Depending on your teacher, they may or may not want you to simplify this a little bit, which isn't that difficult. We just need to do it. So for my first term, 4 times 1/2 to the 0. Again, any non-zero value to the 0 is 1, and 4 times 1 is 4. Okay, plus. For my second term, 1/2 to the first power is 1/2, and 4 times 1/2 is 2. For my third term, 1/2 squared, well, that's 1/2 times 1/2 is 1/4, and 4 times a fourth is 1. For my fourth term, 1/2 cubed is 1/8, and 4 times 1/8 is 4 over 8, which simplifies to 1/2. And finally, 1/2 to the fourth power is 1/16. 4 times 1/16 is 4 over 16, which reduces to 1 over 4. Notice, perhaps not surprisingly, that each term is half of the previous term. And that's because you're increasing your exponent on the 1/2. Every single time, each term is half of the term before it. So hopefully that kind of sort of makes sense and is not completely random. All right. Now, for this question, jumping to our calculator and plugging this in actually wouldn't be that difficult, but the directions do say to use our formula, so we might as well go ahead and do that. So our formula that we developed today says that S of 5, for a partial geometric series, we start... So we start with our A value. So going to our original expression here, our A value is 4, so it's whatever is outside the parentheses. Our R value is what's getting raised to the exponent, which is 1/2. And our N value because we're starting with k equals 1, we can just take that 5 right there. So because we're starting with a 1, we can take the 5. Also, notice that in both the black sum and the green sum, we're adding 5 terms. 1, 2, 3, 4, 5. So those are all of our inputs into our function. So our partial sum, our formula says, we start with a, which is 4. We multiply by our rate, our common ratio, which is 1/2, and we raise that to the n power, which in this case is 5. We subtract another a value, which is 4, over our rate, which is 1/2, minus 1. And this is our answer. All we have to do is clean it up a little bit. So for this one, you know what? To be on the safe side, let's just go ahead and go to the calculator. I'll show you how to type this thing in one step. Now, everyone kind of uses the calculator differently. If you end up doing this a different way, but you end up getting the same answer, I would not worry too much about how you're using the calculator. However, if you get a different answer, you may want to kind of brush up on some of the calculator, sort of tips and tricks, I guess. So we have 4 times 1/2 to the 5th minus 4, and that's all divided by 1/2 minus 1. So if we're going to type this in, if I want to do this in one step, one thing I can do is set off the numerator using a set of parentheses. So my numerator was 4 times, now I'm going to raise 1/2 to the 5th power, and here you really want to be careful when you're raising an exponent, when you're raising a fraction to an exponent. You may find it helpful to include the whole thing in parentheses, which is what I did. And the rest of my numerator was minus 4, close parentheses, and now I'm going to divide by my denominator, so I'm going to include a new set of parentheses, and I've got 1/2 minus 1, close parentheses. Now, if I do this all correct, I should get 7.75. If I want to convert this to a fraction, I've already got the calculator open, so let's just go ahead and do that. And I get 31 over 4. Now, again, there are multiple ways to evaluate this, and some of them may be simpler for you. You may want to do it in more than one step, which is totally fine. No matter how you do this, you should get 7.75 or 31/4. So, getting back to our answer here, we end up getting 7.75 which we just established is the same thing as 31/4, and both of those are our answer in either form. Question 10. Question 10, again, gives us sigma notation, very similar to number 8. In fact, the only difference with number 8 is instead of having a sort of a constant for our upper bound on the sigma notation, we're actually just going to leave it as n. But other than that, it's actually the same thing. So let's go ahead and take a look. Write out the sum. I'm going to do this. Yeah, you know what? There's more space. So we're going to do this. We're going to do this up here because there's a lot more space up here. So A says write out the sum of terms represented by the notation. So we're going to use all this blank space. So we're going to be solving for A right here. So write out the terms. Okay. So our sum from k equals 1 to n of 4 times parentheses 1/2 to the k minus 1. We start with a k value of 1. That's what our sigma notation tells us. So 4 times 1/2. We plug in a 1. 1 minus 1 is 0. Our next term after 1 would be a 2. So 4 times 1/2. 2 minus 1 is 1. After 2, our next input would be 3. So we get 4 times 1/2. We plug in a 3. 3 minus 1 is 2. And this continues. Now, when does it stop? Well, it stops when our k value is n. Well, okay, what is n? Well, n could be anything we want, right? N could be 10, it could be 100, it could be a billion, right? So we don't really know what to do with our last term, so let's just go ahead and plug it in. So our last term is simply going to be 4 times 1/2, just like we've always done. And when we plug in now for k, we simply get n minus 1, which we obviously can't simplify, right? If n was 10, that would become 9, but we don't know what n is, so we kind of have to leave it like that. So that's our answer. Now, depending on what your teacher is looking for, we can, maybe clean this up a little bit. Our first term is 1/2 to the 0. Again, any non-zero value to 0 is 1, and 4 times 1 is 4. Our second term, 1/2 to the first power is 1/2, and 4 times 1/2 is 2. So this is plus 2. Our third term, 1/2 to the second power is 1/4, and 4 times a fourth is 1, plus ... plus. And then our last term, we really can't clean this up in any kind of obvious way. We kind of have to just leave it like that. And that's our answer for part A. So go ahead and put a box around that, I guess. Part B. Once again, use the formula you derived in class today for the sum of a geometric series to find the total of the sum of terms without adding each term individually. So, for part B, we know that our sum, when our partial sum for n terms, our a value is the coefficient, which we already saw is 4. Our ratio is the thing that is being raised to the exponent, which is 1/2. And then the number of terms is n. We don't know what it is. We're intentionally leaving that sort of vague and undefined. Sorry, I shouldn't say undefined, but undetermined. And then minus a, which again is 4, over 1/2 minus 1. That is our answer. Now, unfortunately, we can't really jump to the calculator here. So depending on what your teacher is looking for, you may or may not need to sort of clean this up a little bit. So you may be able to stop there. The rest of this I'll do in green. If you clean this up, one thing to notice is that in my numerator, I can actually factor out a 4. So if I factor out a 4, I'm left with 1/2 to the n. And when I factor out a 4 from -4, I get minus 1. So that's my numerator. And then my denominator, I have 1/2 minus 1. Well, 1/2 minus 1 is simply negative 1/2. And again, depending on your teacher, this may or may not be necessary. What I can do now is I can actually do this division. I can do 4 divided by negative 1/2. If you don't know what that is, I would do that on the calculator, and I would just do 4 divided by parentheses negative parentheses 1 over 2. And what you'll end up getting is negative 8. And then everything inside the parentheses stays the same. And then if you want to get really fancy, if you want to get rid of your negative, you can distribute the negative, but you can leave the 8 out front, giving us 1 minus 1/2 to the n. All of that is technically correct. It just kind of depends on what it is that your teacher is looking for. So if you want an unsimplified version, what is written in black would be fine. If you want a simplified version, I would go with what's in green. Question 11. Question 11 says, based on problems 8 through 10, estimate the sum of this geometric series, where segment goes from k equals 1 to infinity times 4, or of 4 times 1 half to the k minus 1. So we didn't do question 9, but I think it's still going to be okay for us to take a look at this problem. So all we have to really do for question 11 is to sort of think about what is going to happen, if we take our answer, let's use our sort of final, like sort of fancy version for number 10. Let's just take a look at this final answer here. And, sort of think about, I'm going to do this in kind of a weird color. We'll say purple. And what would happen if we were to take that formula, and let's say we did 8 parentheses 1 minus 1 half. Now I'm going to do something that's not really great here. I'm actually just going to go ahead and plug in infinity for a second, and maybe I'll put this in like air quotes, because this isn't great math. You're not really supposed to plug in for infinity. Infinity's not a number. It's a concept. It doesn't have any of the real properties of numbers. So I'm putting this in quotes because it's not really like great math, but I do think that it's valuable in sort of thinking through what would happen here. If you think about this piece right here, well, instead of infinity, if you raised 1 half to the first power, you'd get 1 half. If you raised it to the second power, you get 1/4, which is smaller. If you raise it to the third power, you get 1/8, which is even smaller. If you raise it to the fourth, you get 1/16, which is even smaller. So what ends up happening here is that as your exponent gets bigger and bigger and bigger and bigger, the result gets smaller and smaller and smaller and smaller. And in fact, if you were to just take your calculator here, and if you could say, well, what is 1 half to the, I don't know, what's to the 10th power? Okay, well, that might be difficult to read, but when you have e to the negative number, that's a really small number. That's what that means. And this might just get even more confusing if it's going to be more scientific notation or exponential notation, which it is. So if you're not that good at reading exponential notation, this might not make sense. But as this e to the negative whatever, as the negative number increases in magnitude, your number is getting smaller because you keep multiplying by 1 half. So if you think about what's happening here, if you were to somehow magically plug in infinity, which again we can't do, but if you could plug in infinity, this piece is actually going to go away. It's going to become 0, and you're left with just 8 times 1. 8 times 1 minus 0, which is 8 times 1, which is 8. So instead of sort of getting kind of lost in the weeds here about sort of how to handle infinity, which is beyond the scope of this class, we really don't want to sort of deal with infinity if we don't have to. Instead of sort of figuring out, well, how could we plug in infinity, just think about what would happen if you plug in increasingly large values here, and hopefully sort of conceptually you can see how the 1 half is going to go away, and we're eventually going to be left with just 8. You could do something similar with our original problem in B. You could go all the way back to this one and sort of do the same thing. The 1 half to infinity is going to become 0, so your numerator simplifies to -4. Your denominator is -1 half, and -4 divided by -half is also positive 8. So it would work even if you go back to the original unsimplified version. But if you use the simplified version, which is in green, then hopefully for number 11, this estimation makes a little bit more sense as to why this is going to converge to a final answer of 8 as your n value gets increasingly large for this summation. to in geometry, and there's a lot of angles that get formed by this. There's 4 angles there, and there's 4 angles there, and there's a lot of different relationships that exist. And it turns out that this angle here, which is EAB, is actually going to end up being congruent to that angle there, which is EDC. And we're going to say my claim first, and then I'll sort of explain the reason. So the angle up top is angle EAB. And when you have this kind of construction, that angle is congruent to EDC. Now we have to be able to explain why. Why are these 2 angles congruent? So these 2 angles that I've indicated with 2 curved lines here, they are what are called alternate interior angles. So there's kind of 2 pieces of information here. There's alternate. Now, the reason why these are considered alternate is because, maybe I'll do this in purple. So you have one angle that's to the right of the transversal, and you have one angle that's to the left of the transversal. That's what makes them alternate. So one's on the right, one's on the left. That means that they're alternate. And also, both of the angles are between the green lines. So notice how the 2 curves at the top are it's below the top line, and the 2 curves at the bottom are above the green line. That means that they are interior. Now, this would be different from angles that are, say, in this area and this area, which would be exterior. Okay, but let me get rid of all that extra stuff. So these 2 angles that we just indicated, they're what are known as alternate interior angles. And when your green lines in this situation are parallel, which they are in this case, alternate interior angles are congruent to each other. So if I get rid of everything extra here and I leave just my sort of symbols, notice that each triangle, ABE at the top as well as DCE at the bottom, both angles have one pair of congruent sides, and each side is sort of flanked on both ends with congruent angles. So the congruent side is between the 2 congruent angles, and so this is angle, side, angle. So now I can basically just jump to my very last step, and I'm just going to rewrite the thing that we're trying to prove, which is that triangle ABE is congruent to triangle DCE. And as we've already discussed, the reason that we're allowed to say this is that in this situation, we have the angle, side, angle triangle congruency situation. So that is one of the acceptable ones, and so that's the one that we're going to go with, and that is our proof for number 12. Question 13. Question 13 says, prove that triangle CBF is congruent to triangle DBF. And we are told that BF is perpendicular to CD, and we're also told that F bisects CD. Now our picture's on the next page, which is a little annoying here. I'm not going to scroll back and forth constantly, so I'm just going to leave it on this page. But you're welcome in your book to kind of, look at the given statements, look at the picture, and we'll just kind of go from there. So again, what we want to do here is we want to make a series of claims. And for each claim, we have to have a reason. And what we want to do is we want to build towards one of the aforementioned triangle congruency scenarios that we've established. So basically, that's everything other than angle, 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 or side, side, angle. Basically, any other combination of angles and sides should work. So, um, we are, like I said, we are given that BF is perpendicular to CD. Also, notice that in this picture, they've actually already gone ahead and included our right angle there, because if BF is perpendicular to CD, then it is going to form a right angle. I'll go ahead and put a right angle there as well, right? So both of them are right angles. Um, and I am going to now. What I will say for some of these triangle congruency proofs, it is possible that the way that I'm going to write it is a little bit different than maybe how you were taught or how your teacher wants you to do it. So it's sometimes okay to have some minor differences in terms of like what gets included, what doesn't get included. If you're ever not sure about whether your proof is sort of an acceptable proof or not, you're always welcome to stop by, talk to your teacher, come by for office hours, and we can sort of figure out, if what you wrote is different than what we're going to discuss right here, sort of whether that is acceptable or not. So I'm just going to go ahead and I'm just going to start by sort of rewriting our given. So we were told that BF is perpendicular to CD. And the reason that we're allowed to say that is that that was given. Now, depending on your teacher, depending on your class, depending on other factors, you may or may not need to explicitly state that angles BFC and angles BFD are in fact right angles. I think for this problem, I don't think that that's strictly necessary. I think that given that they're perpendicular, it's kind of implies that they're right angles, that they're 90 degrees. However, your teacher may require you to explicitly state that the two angles in question are in fact right angles. But whether you do that or not, sort of the next thing that we can say is that, well, all right angles have a measure of 90 degrees. So they're all congruent. Because if two angles have the same measure, they are congruent. That's the only thing that needs to be true for congruent angles. So because angles BFC and BFD are both right angles, that tells us that angle BFC is congruent to angle BFD. And the way that I would phrase this is that this is basically the definition of perpendicular. And now, again, depending on your teacher, you may need to include a couple more things here. But for me, I think that this is sufficient to say that, all right, well, if these two lines are perpendicular, we know that means that they form a right angle. All right angles are congruent. Therefore, these two angles in question are essentially the same angle. They are congruent. Okay, so that gets us an A. So that's great. We are also told that F bisects CD. Clean that up. Bisects CD. And the reason that we're allowed to say that is that we were also given this information. Now, what does it mean to bisect? Well, bisect means to cut in half. So if F bisects CD, it means it cuts it in half, which means that CF is congruent to DF. So I'm going to go ahead and say that. CF is congruent to DF, and that's really just the definition of a bisector. It cuts it in half. If it didn't cut it in half, it wouldn't be a bisector. All right, so we have S and A in either order, essentially. So at this point, we need at least one more thing in order to say that these two triangles are congruent, the triangle on the left and the triangle on the right. And notice that BF is in both triangles. BF is a side of triangle BFC on the left. It is also a side of triangle BFD on the right. Well, one of the sort of, I would say, simplest things to understand in arguably like all of geometry is that anything is congruent to itself. So side BF, unsurprisingly, is congruent to side BF. It's the same thing. Except in this context, we're just saying, all right, well, on the left, BF is a side of the left triangle, and on the right, BF is a side of the right triangle. And the name of this property in mathematics is called the reflexive property. In geometry, this is known as basically just saying x equals x. So 7 equals 7, 4 equals 4, pi equals pi, et cetera, et cetera. So that's the reflexive property. So notice that in our picture here, we have two triangles, the triangle on the left and the triangle on the right. And in both triangles, we have a pair of angles that are congruent, namely the right angles, and each of those angles is sort of spanned on the left and the right by a side that's congruent. So to the left of each right angle and to the right of each right angle in each triangle, you have a side that is congruent to a corresponding side in the other triangle. So what we have here then is we have side angle side, which allows us to finish our proof. Specifically, triangle CBF is congruent to triangle DBF. And as we've said, the reason that we're allowed to say that is that we have established the side angle side congruency situation for two triangles, which is an acceptable congruency situation. So this probably should be more or less what your proof looks like. If you have an extra line or you're missing a line, I would say just follow up with the teacher just to check and see if your proof is still acceptable. Because even if you don't have this exactly, it is possible that your proof is correct. But this is sort of how I would do this problem. Question 14. Question 14 is saying, actually, we have to fix something with question 14. So before we do anything else, hopefully this was already fixed in class, but this should say, the second triangle should say ADC. So let's just go ahead and just sort of pretend like it always said that. And now we're going to move on with this problem. So 14 says, prove the triangle CBA is congruent to triangle ADC. And we have a triangle here. We have a quadrilateral, really, that looks like a rhombus, but maybe is or is not a rhombus. I don't have enough information to tell. It looks like a diamond. But it's definitely a quadrilateral. We've got some parallel symbols here. So this is parallel to this, and also this is parallel to this. And what we've done is we've taken this quadrilateral and we split it up into two triangles, and we are asked to prove the triangle CBA up top is congruent to triangle ADC on the bottom. As always, we're going to do this by making a series of claims, building towards our proof. And for each claim, we have to have a reason. We can't just like randomly say stuff without being able to back it up. That's what makes it a proof. So again, whether you need to say this or not is kind of dependent upon your teacher. Just to be safe, I'll go ahead and include it. So our picture tells us that BC is parallel to AD. And our picture also tells us that BA is parallel to CD. And the reason that we're allowed to say that is that this was given information to us. So, all right. So BC is parallel to AD, BA is parallel to CD. Notice that ABCD is obviously a quadrilateral. It's a four-sided figure. So what we have here is we have a four-sided figure with two pairs of parallel sides. Well, that tells us that quadrilateral ABCD is a... So quick check here. What is the name of a quadrilateral that has two pairs of parallel sides? That's right. It's a parallelogram. Good job. And the reason that we're allowed to say this is that this is the definition of a parallelogram. Now, parallelograms have a lot of sort of properties and characteristics. But at its most basic level, a parallelogram is simply a four-sided figure with two pairs of parallel sides, which is exactly what we have here. So we're dealing with a parallelogram. That's great. Well, one of the aforementioned characteristics of a parallelogram is that opposite sides are congruent. So and specifically the sides that are parallel are congruent to each other. So what that means is because BC is parallel to AD in this case, it also tells us that BC happens to be congruent to AD. And we also know that BA is congruent to CD. Fix that a little bit. CD. Okay. And the reason that we're allowed to say that is because now that we've established that this is a parallelogram, one of the characteristics of parallelograms is that opposite sides of a parallelogram are congruent. So that tells us that AB is congruent to CD and BC is congruent to AD. Awesome. Now we just need one more thing to say about this figure. And there's actually a lot of different directions that we could go in right now because there's a lot of different properties of parallelograms that we can use. However, I think the easiest, let's not overthink this. Notice that side AC in the middle is a side length of both triangles. AC is a side of the top triangle. AC is also a side of the bottom triangle. Well, as we've seen in geometry, any figure is congruent to itself, right? So AC is the same thing as AC. Hopefully that's obvious. And the mathematical name for that is the reflexive property. So 3 hash marks. Now notice that in the top triangle and in the bottom triangle, we have not 1, not 2, but 3 pairs of parallel sides. That means we have side, 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 or SSS. That is one of our acceptable triangle congruency scenarios. So that means I'm going to jump to the thing that we're trying to prove, which is CB, or triangle CBA is congruent to triangle ADC. And the reason that we're allowed to say that is that we have established that side, side, side applies to this situation. So we have 3 pairs of congruent sides, therefore our 2 triangles are congruent, and we are now done question 14. There are other ways to do 14. It turns out that in a parallelogram, opposite angles are also congruent. So you could have done side angle side here, and that would have also been correct. And then dealing with the other angles, I mean, you could deal with the other angles, but it's more work, so I wouldn't recommend that. I would recommend either doing it this way or doing it the way that we did in the actual problem. There are other ways, but in my opinion, I think that they're more complicated. Question 15. Question 15 says, prove that triangle KHM is congruent to triangle EFG. Again, we're on the next page. It's a little annoying. So we're just going to stick with this picture. I'm not going to scroll back up and down. As always, we'll make some claims. We'll have a reason. And we're going to build towards one of our acceptable triangle congruency situations. Now, this is kind of a weird problem because they sort of tell us everything that we need to know visually. So notice that they're telling us in the picture that side KH on the left is congruent to side EF on the right. That's what the single hash mark means. And the reason that we're allowed to say that is that that was given to us visually in the picture. The picture also tells us that angle M, and we only need one letter here because when you say angle M, it's kind of, quote, obvious what angle you're talking about. So I'm only going to use one letter here. Angle M is congruent to angle G because they both have one curve, sort of representing that angle. And the reason that we can say that is that we are again given this information. It's in the picture. Our third statement is that angle K up top on the left is congruent to angle E on the right. You can notice it has two curves at the angle. And the reason that we can say this is that, yet again, we're given this information. So we're given a whole lot here. Notice that now what I have is I have two pairs of congruent angles and one pair of congruent sides, and notice that my congruent side is not between my congruent angles, right? If it were, it would be over there, right? But it's not, so I'm going to get rid of those. It's not between my two congruent angles, which means this is not angle, side, angle, but it's angle, angle, side. Ultimately, it doesn't really matter, at least on the left, because at this point we can actually jump to the thing that we're trying to prove, namely that triangle KHM is congruent to triangle EFG. EFG. And that's because we've established the angle, angle, side congruency situation for these two triangles. So in this case, we're just basically given what we need to know. We don't really have to do many calculations or too much extrapolation of data. We have angle, angle, side, and that is our proof.